All right, let's just jump right in. If you've ever poked around a Linux terminal, you've definitely seen this /dev directory. It is packed with all these weird looking files that are supposed to be your hardware. But how does that actually work? How does a file become a piece of hardware? Well, today we are going to crack that code and really unravel the magic behind a Linux device driver.
So take a look at this. This should seem pretty familiar to anyone who's run ls-l in /dev. You've got your permissions, the owner, but hang on a sec. Right where you'd expect to see the file size, you've got these two numbers, 1, comma 3. And check out that very first letter. It's a C. What's that all about? Well, that C actually stands for character device, and those numbers are the key to this whole thing. So that's the big mystery we're going to solve today. What are these special files, and what is the secret code that's hiding in those two little numbers? To figure it all out, we're going to start with that mystery in dev. Then we'll meet our guide for this journey, a driver called Skull. From there, we'll decode what I like to call the kernel's address book, see how a driver gets its number, understand the contract it makes with the kernel, and finally, we'll look at the critical bridge between your programs and the kernel itself. You can't go on an adventure like this without a guide, right? And for our trip deep into the kernel, our guide is going to be a fantastic little driver named Skull. It is the absolute perfect companion for figuring out how this whole system works. So first things first, what are we even dealing with here? Well, Skull is a character driver, and the beauty of this concept is just how simple it is. Seriously, think of it like a water pipe. Data flows in, data flows out, one byte after another. There are no complicated blocks or sectors to worry about, just a simple, clean stream of data. And the reason Skull is so perfect for this is because it's completely software-based. It doesn't talk to a real physical piece of hardware at all. Nope. It just manages a little chunk of computer memory. And this is great for us because it lets us focus completely on the driver's logic and how it talks to the kernel without getting bogged down in messy hardware details. Okay, let's get back to those mystery numbers, the 1 and the 3. These numbers are at the very heart of how the Linux kernel keeps track of everything and finds the right driver for the right device. You can really think of it as the kernel's own internal address book. So here's how it breaks down. That first number, that's the major number. It tells the kernel which driver to call. It's like the street address for a big apartment building. The second number is the minor number. This tells the driver which specific device you want. It's the apartment number inside the building. So a device like dev/null and dev/0 can share the same building address. That's major number 1. But they're totally different apartments, each with its own unique minor number. Now, you might think the kernel is juggling these two numbers all the time, but it's actually a bit smarter than that. It uses a handy macro to combine them into a single, special data type called dev_t. This is just a really clean and efficient way to pass the device's complete address around inside the kernel. Okay, so we know what the numbers mean, but where in the world do they come from? I mean, a driver can't just show up and pick any number it wants, right? It has to go through the proper channels and officially request an address from the kernel. And there are basically two ways to do this. The old way is called static allocation. That's where you basically tell the kernel, hey, I'd really like to use major number 240, please. It's super risky because what if another driver is already using it? The modern, much more polite and strongly recommended way is dynamic allocation. Here, you just ask the kernel, could you please give me a free major number? And it hands you one that is guaranteed to be available. No conflicts, no mess. And hey, don't just take my word for it. The folks who actually write the Linux kernel are very, very clear about this. Dynamic allocation is the right way to do it. It keeps your driver from stepping on anyone else's toes and helps the whole system run smoothly. All right, so our driver has its unique address. Awesome. But the kernel still has no idea what our driver can actually do. To solve this, the driver has to give the kernel a sort of contract, one that clearly spells out all the services it offers. And it's a brilliant piece of design. This contract is a special structure in the C programming language called file_operations. And it's basically just a list of functions. It's like a switchboard. When your program tries to read from your device file, the kernel looks at this contract, finds the entry for .read, and connects the call to the exact function your driver provided for it. Let's look at a few of the most important clauses in this contract. First, .owner. This one is absolutely crucial for stability. It basically tells the kernel, hey, don't unload me while someone is using me. Then you have the big ones, .open, .read, and .write. These are the workhorses where you put your code for setting up the device, getting data from it, and sending data to it. And finally, .release, which is your chance to clean everything up once the last program is done with the device. The very last step is to make it all official. The driver calls one last function, cdev add, and it hands the kernel both its device numbers and its file operations contract. The second that call succeeds, poof, the device is live. The kernel now knows its address, and it knows exactly what that device can do. So we've done it. We have a clear path from a command like read or write all the way down to our driver's code. But there's one final, absolutely critical piece of this puzzle we have to solve. How does the actual data get across the heavily guarded border between a user's program and the kernel's protected memory? See, the kernel cannot, under any circumstances, just blindly trust a memory address that a user program gives it. I mean, think about it. It would be a gigantic security hole. A bad pointer could also point to memory that's been swapped out to the hard disk. And if the kernel tried to access it directly, bam, the whole system would crash. This strict separation is fundamental to how a stable operating system works. So, to solve this, the kernel gives us two special, heavily guarded functions that act as a secure bridge. To get data out of the kernel and back to your program, like in a read operation, the driver must use copy to user. And to bring data in from your program, like in a write operation, it must use copy from user. These functions do all the hard work and check everything to make sure the transfer is completely safe. So let's put it all together. Let's trace the journey. Your program calls read on /dev scal0. The kernel sees the major and minor numbers and finds our scal driver. It then looks up the .read function in the driver's contract and calls it. Inside that function, our driver gets the data ready, and then it uses copy to user to safely pass that data across the bridge and back into your program's hands. And there you have it. We started with a confusing line of text in a terminal, and what we've uncovered is this incredibly robust and really elegant system. A system built on unique addresses, clear contracts, and secure bridges that allows all of your applications to talk safely and reliably to all the hardware in your computer. It's amazing stuff. It really makes you think, doesn't it? The next time you type a simple command, just take a second to appreciate the incredible engineering that's happening right beneath the surface. It makes you wonder, what other commands that you use every single day are hiding this much complexity and this much elegance?